Okay, so end of chapter 23 questions.
Yeah. Do you want me to give you the list of them, or just we'll go through one by one?
One by one.
Okay. Number 67. I just want to be sure I have these reactions down pat.
Let me see something real quick. Okay, that's one that I don't have written down. Let's take a look. Page 1100 and something, right?
1110.
Wow, we went through the whole book, huh? Okay, so let me change my share so that people can see the question. So number 67, and this is more for people to just get their footing. I'll read it. What is the structure of the product from the reaction of butanoic acid and methylamine? To what class of compounds does this belong? We'll answer that for the reactants and the product and write a balanced equation for the reaction. Okay, so I'm going to kind of write out what they want in number 67. The product of butanoic acid and I got to find it again. Methylamine.
Yeah.
Functional groups. And then a reaction equation. Okay, so I'm actually going to start with the reaction equation, but I'm going to start by understanding how to draw butanoic acid. So butanoic acid is going to have 4 carbons because of the but. And oic acid means that you have to have a carboxylic acid.
Yeah.
Now you can put it on the beginning, which is probably where it belongs, but I like to put it over here when I'm doing a reaction like this. So even though it looks like I've made the compound longer, it is still only 4 carbons long.
So is it okay if that I put mine on the carbon 3 and then the OH at the end?
No, because then that would be propanoic acid. So I think, and correct me if I'm wrong, you're describing to me, you're describing to me something that looks like this, or maybe like this. Is that right?
Yeah, but I did a little tail for the OH to account for the 4 carbons.
Somewhere in here?
No. At the end of carbon 4 or 1, whatever way you want to look at it.
So here's carbon 4.
I did another line to OH to show that OH was on 4. Yeah.
And where is the double bonded carbon?
On that valley before OH.
Right here?
Yeah.
Yeah, that's the same thing as this.
Okay.
They're exactly the same things, just one's flipped. That's all.
Okay.
Okay?
Yeah.
Okay, now methylamine means that you're going to have a nitrogen bonded to a CH3 and 2 hydrogens.
Yeah.
Okay? Now, when you put these together, what is going to happen is this OH and this H are going to form water.
Water. Yeah.
The other 2 pieces you simply slide together. So here are the other 2 pieces. where we slide them together. So this is now going to bond to nitrogen. And I'm going to put the CH3 kind of going up at an angle like that. And then H2O.
Okay, great.
Now, the product is called an amide. And the amide is because you have this right here, a carbonyl and bonded to a nitrogen.
Right.
This is an amine, and you would want to circle a carbon and a nitrogen. And this is a carboxylic acid. And you'd want to circle all of this for your carboxylic acid. And this is the reaction equation. It shows the functional groups and you get the product.
Perfect.
Now, there are other ways of showing the reaction. You could do this. So this is butanoic acid, basically carbon by carbon.
Mhm.
For this guy here, what you would normally do is this or this. More often you do it this way at the bottom. What kind of structures or formulas are these called?
Condensed.
Very good. And this one would look like this. Okay? Okay, that's a good one. What kind of reaction is this called, do you know?
Condensation.
Condensation, that's right. And really, it's called a condensation because you're taking two larger things and condensing them together.
And water.
What I always like to think of as a condensation because one of the products is water.
Yeah.
Okay, what would you like to do next?
Number 81.
Number 81. So 81 reads as follows. Write equations for the following reactions representing the reactants and products using structural formulas. A, the reaction of acetic acid and sodium hydroxide. The reaction of methylamine with HCl. Okay, so 81, show reactions using structural formulas. So this is basically a Lewis without showing the lone pairs.
Yeah.
Okay, so we've got acetic acid, and sodium hydroxide. Now, we know that the formula for acetic acid is CH3, COOH, and we know that the formula for sodium hydroxide is this. And what happens here is that the hydroxide from the base and the hydrogen from the acid make H2O. So this is an acid plus a base make a salt and water.
Got it.
Here is the salt. Now, normally you write the sodium at the front for an ionic compound. So here are the structural formulas of each of these. Now for sodium, the only thing we can do is put a plus on this and then plus an OH with a negative on the oxygen.
Okay.
Now, the reason for that is because it's an ionic compound, and we know sodium's an ion, and we know OH is the hydroxide ion.
And since it's a strong base, we know it's going to disassociate.
Oh, yeah. Because it has sodium on it.
Yeah.
Okay, so how do we draw the this guy here? Draw it like that to begin with, like that. And oh, I made a mistake. You should have an O here also. Two O's.
Oh, yeah.
And then an O here, and then a negative on it. And then I'm going to put the sodium here because these are oppositely charged ions. And then I'm going to do this. I'm going to make an HOH. And I'm not trying to show any 3D on it or anything like that, any bond angles. I'm just trying to show how things are connected and the charges on things.
Okay.
So what I tried to do was start with what we do know from the past and bring it to the present.
Okay.
Okay, letter B. Are you ready for letter B?
Yeah.
The reaction of methylamine with HCl. So this is kind of a new one to us. This is actually an acid and a base also. The methylamine is the base.
Nitrogen.
The nitrogen, that's right. So here's the methyl. And here's the amine.
Right.
And here's the HCl. And again, we're not showing any lone pairs.
And okay, so okay, I can guess that we're gonna make NH3.
Yes, but we don't write NH3
No.
because we are showing all of the bonds.
Okay.
And what is left over?
The chloride ion.
Yeah, now if that's the chloride ion, what must be true about this guy right here?
That it has a positive charge.
Where do you think it is? It does, and where do you think it is?
Oh, on that hydrogen that we gave.
Actually, it's on the nitrogen.
Oh.
Think about the formal charge on the nitrogen. It would be the group number, which is 5, minus half of the bonding electrons, which is 4, minus all of the non-bonding electrons, which it has none of. So 5 minus 4 is plus 1.
Okay. Cool.
How do we know that the nitrogen should have some sort of charge on it? And the simple answer is, if it had 3 bonds like it normally does, it probably shouldn't have a formal charge. But if it has 4 bonds or 2 bonds, it probably should have a formal charge.
Yeah.
Kind of like the chlorine, it normally likes 1 bond, right?
Mm-hmm.
Now it's got none. It should probably have a formal charge.
Okay.
So that's kind of a way to gauge whether something should have a formal charge. Does it have the number of bonds it normally makes?
Yeah.
What is that behind you? I've got a little small window. Is that a motorcycle or a bicycle?
Probably the stroller.
Oh, a stroller.
Yeah, this room is a mess right now, so we've got all of our extra stuff in here.
It looked to me like a motorcycle. Okay, what would you like to do next?
I think 83.
Number 83. Let's see if that goes and bleeds on to the next page. It does not, thank goodness. Okay. So here's number 83. Write an equation for the formation of the following polymers: polystyrene from styrene and polyethylene terephthalate from ethylene glycol and terephthalic acid. Okay. Write equations, basically write reactions.
Yeah.
A, we're going to make polystyrene from styrene. And they tell us that styrene looks like this: C6H5 CH2. Now, when you see this double bond, we're going to have what's called an addition polymer. And it's a carbon-carbon double bond. And the best way to draw the product is to start with the double bond like this, and to take these pieces that are on that carbon and write them like this: C6H5H.
Take the pieces. Oh, I see.
So what am I going to add to the other carbon?
H2.
H and
H.
okay, so you see how I'm writing them separately like that. That's what you want to do.
Okay.
And you're going to put N here. What does that N mean?
However many of those.
However many you have. So here, we're going to polymerize it. And you're going to write this thing again, but I want you to bear with me. And I want you to tell me what is the difference between what I've done on the left and what I've done on the right.
Well, I know you're getting rid of the double bond.
Okay, so there's no double bond.
And you're adding a bond to the carbons.
Okay, so now what you're going to do is you're going to add a bond to each carbon. You're going to put a parentheses through those bonds. And where do we put the N?
As a subscript.
Okay, now this is not a question asked here, but I'm going to ask it. Can you draw 3 units of this polymer?
Yeah, or I can just write subscript 3.
No.
Oh, darn it.
There's 1 unit. There's 2 units. And there's 3 units. So I want to show you something that's kind of interesting. Do you see how this is the repeating unit again and again and again?
Yes.
I'm going to add a 4th one here. And you'll see why in just a moment. And that's not supposed to be an H. Do you see how that is the repeating unit?
Yeah.
So my point is, we could have written this flipped over like that and still got the same answer. Are you with me there?
Yeah.
Do you understand that we could put the C6H5 going down instead of up?
Right.
So all of those would be correct answers. I've just shown one version of the correct answer. Fair enough?
Yes.
Okay. So for 83B, we're going to make something from ethylene glycol and terephthalic acid. Now, I believe I know what terephthalic acid is. I think it has 4 carbons, but I'm not sure. Ethylene glycol has 2 carbons. So this is ethylene glycol.
Are we supposed to know what that is?
No, you should look them up. So in our index, let's find out what it says about ethylene glycol, okay?
All right.
Um,
Sounds like it's going to be a alkene.
the name makes it sound that way, but it's not,
Okay.
because it's a common name. So ethylene glycol is on page 1083. So if you go to page 1083, you will see a molecule where do they talk about it?
Well, I see
Ethylene glycol and glycerol are common alcohols having 2 and 3 groups respectively, and ethylene glycol is used as this. What they don't tell you about ethylene glycol on page 283 is that oh, there it is. Look on page 284. Do you see a picture about just above the middle of the book where it says 1,2-ethane diol?
Yes.
That's how we would name it. So ethane because 2 carbons, diol because 2 alcohols, and 1 and 2 because the alcohols are in carbons 1 and 2.
Got it.
Ethylene glycol is a common name. Fair enough?
Yeah.
Okay, now if we look for terephthalic acid, chances are when we go to the carboxylic acids, we'll see terephthalic acid somewhere. And I'm still looking.
Me too.
Oh, I was wrong. Terephthalic acid is with a benzene in the middle.
Really?
So here, when they asked us to write out the reaction, they did not say structural formulas or anything like that. So I'm going to write these in a way that is going to help us figure out what's going on. And so I'm going to redraw this guy. Like this. Okay, so here I've run out of room to put these guys together, but we have N of these and N of these. Now what's going to happen is that this is going to combine with an OH from the carboxylic acid, and this will too. So you want to redraw your alcohol like this.
So we're losing OHs.
Now we're going to lose OHs from here to help make the water. So you can see we lost 2 hydrogens, we lost 2 H's, 2 OHs, so we're making H2O.
Okay.
Now, if we start off with N of these and N of these, how many of these are we going to make?
And
N. And where do you want to put the parentheses?
so the whole thing is repeating.
The whole thing is repeating.
Okay, so around the whole thing.
Now, what is another correct answer? I'm going to show you another correct answer. Are you ready for that?
Yeah.
So what's the difference? I put the diacid first instead of the diol. That's all.
So from the ethylene glycol, which is an alcohol,
Right.
we lost the H's, and then from the acid, we lost the OH.
Right. It's just like the condensation reaction we
Yeah.
did earlier, only earlier we did it with an amine. Here we're doing it with an alcohol. So this is an O instead of a nitrogen. So this is an O instead of a nitrogen here. But what makes this a polymerization reaction is that rather than only have one alcohol and one acid that can react together, each molecule has two acids and two alcohols, so they can react on both ends and basically become part of a chain.
Yeah. Okay.
Any question about that?
I mean, for an exam, are you going to give us names like ethylene glycol, or is it going to be something?
I may, but I would give you the structure too.
Okay.
Because I don't expect you to know these molecules.
Okay.
Okay.
All right.
What next?
86.
86.
It has a red triangle.
Oh, that means it's really hard. I don't know how to do those.
I have faith in you.
Structural, well, the answer's in the back of the book, right?
Not
No, that's
that one.
structural.
Even.
Draw all the isomers of C3H8O and give the systematic name and class. Name,
Class.
class. Class means functional group.
I thought.
Okay, so what do you think I'm probably going to start with?
Propane.
Yes, I am.
Okay.
I just had a little. My mic is, or your mic, my speaker isn't working very well.
Okay.
So when you said propane, I thought you said cocaine. I was like, what is she talking about?
Oh man.
What am I going to start with? You start with cocaine,
Some people do.
I guess. Not in my house.
Mm-mm.
Okay. Now I need to put an oxygen on this somewhere. Should it be a single oxygen or a double bonded oxygen? And here's what we're going to do. We know that C3H8 would be like an alkane, right?
Yes.
Yeah, right?
Yes. 2N plus 2. Yes.
Now, how do we keep eight hydrogens and add an oxygen?
Well,
What are we can do it?
I don't know. That's what I was confused about.
Chances are we don't want to put a double bond on there, because if we put a double bond on there, we'd only have 6 double bond anywhere on this, or a double bond on oxygen. We'd only have 6 hydrogens, right?
We would lose. Yeah, we would lose 2 hydrogens.
So we got to think of a way to put oxygens on here without using a carbon oxygen double bond.
So just put an oxygen on there.
Oh, well, we could. Where do you want to put it?
On the middle.
First, second, or third carbon.
The second.
Okay, there's an oxygen. We don't have anything that does that. So what do we have to do here? Plus, we just took away a hydrogen. Now there's only 7 hydrogens.
Well, could we make an alcohol?
There you go.
Okay.
Now, could we do another one of these?
Yeah.
Where?
2
or 3?
1.
Okay, so I'm going to put the H to the left because it looks better that way than to the right.
Okay.
So you can, write HO or OH, it doesn't matter. The key is, though, make the bond go to the oxygen, not the hydrogen.
Yeah.
What do you think this would be called?
The top one?
Yeah, the proper name.
The property.
Proper name.
Oh, propanol?
Yes, but more than that. Because this is also propanol, right?
2-propanol?
Correct. And the bottom one?
Would that just be propanol?
No, 1-propanol.
Okay, so we do distinguish that it's on carbon 1.
Yep, because it will not always be on carbon 1. The only time we would not say is when it's on a specific carbon, like ethanol. Would you say 1-ethanol? And the answer is no, because it's on carbon 1. There's only
Yeah.
2 carbons. It can't be on 2. That's why it's called ethanol.
Okay.
Okay. Do you know the common name for the one above?
Isopropyl.
Isopropanol or isopropyl alcohol.
Yeah.
Usually it's called isopropyl alcohol when you buy it as a product in the store.
Yeah.
Okay, so are there any other alcohols we can make with this?
No.
Well, then that's a problem. What other things can we do with the oxygen and make this work? Now, we can't do any carbonyls. We can't do esters, carboxylic acids. What other functional groups have an alcohol in them?
In ether?
Ether. Let's see if an ether will work. So here, what's the key to drawing an ether?
I don't know. I just know we need an oxygen and the rest doesn't matter.
The oxygen has to be between 2 carbons.
Okay.
So here, if I
on
add
carbon
a carbon to an oxygen, and then that's 2 carbons and 1 oxygen, okay?
Yeah,
How many carbons do we need?
3.
So I'm
So
going to do that.
we can,
Is this going to be enough hydrogens, though?
H3. Yeah.
This will be perfect. So what do we call this? We call this ethyl, methyl, ether.
Why ethyl?
This is a 2-carbon unit, which is an ethyl.
Yeah.
So,
Oh, methyl.
and then methyl, ether. Why does ethyl go first? Is it because it's a longer piece?
No, because it's an alphabetical order.
Because it's an alphabetical order.
Okay.
So what are the functional groups of these guys? The first 2 that we did.
Alcohol.
Alcohols. And what about this last one?
Ether.
And heck, the name even tells you it's an ether, right?
Yeah.
And the name here strongly indicates that it's an alcohol because it's all.
Mhm.
Okay, so that's 86A. B. I really like this section. This was kind of like my forte in grad school.
Organic chemistry.
What's that?
You mean organic chemistry?
Yeah, I was kind of like a biological organic chemist in grad school.
Mhm.
Draw the structural formulas for an aldehyde and a ketone. Oh, now they're asking for structural formulas.
I don't like that.
Aldehyde ketone.
Is it saying that that's one compound with an aldehyde and a ketone, or is it saying aldehyde plus a ketone?
One of each, because for an aldehyde, you need to have a carbon double bonded to an oxygen, right?
Yeah.
And for a ketone, you need to have a carbon double bonded to an oxygen. So that would be two oxygens if you have them both in the same molecule, right?
Yeah.
But the formula they give us only has one oxygen.
Okay.
So by default, this has to be the formula for the aldehyde and the formula for the ketone.
Okay. So we're gonna start with butene.
Yeah, and since they say structural, I'm going to put 4 carbons in a row, just like that.
Well, can we do line drawing too?
Not when they say structural formula.
Not just for practice.
Well, just for practice, then we do this.
Yeah.
So for an aldehyde, where are we going to put the double bonded oxygen? On one of the ends.
It has to be one of the ends.
Yeah, because we also have to have a hydrogen bonded to that carbon.
Right.
If I put it here, is that going to be an aldehyde?
No.
No, but how about if I put it here? Is that going to be an aldehyde?
Yeah, because there's a
And I'd
hydrogen.
like to really get people to see it by putting the H there. So it kind of pops, right?
Okay. Yeah.
So these are structural formulas of an aldehyde and a ketone with the formula C4H8O, I believe, but we're going to double check. How many carbons here on the top one?
4.
How many oxygens?
1.
And how many hydrogens?
Only 7.
How many here at this end?
3.
How many at this end?
2.
Why
3.
say 2, 3, right?
Because I expected you to go to the peak.
Oh, and then how many on the peak?
2.
So 3, 3, and 2 are
7. Oh, 3, 3, and 2. 8. So that's okay. But it's not an aldehyde, it's a ketone.
So this is a ketone, and it would be called butanone.
Butanone. Okay.
And we don't have to tell people where the ketone is because it's on carbon 2, period.
Yeah.
Now this is an aldehyde. What would we call this guy?
Butanol.
Butanol is an alcohol.
Right.
So I want you
Butanol.
to, if you're from the East Coast, get kind of nasally and say butanol.
Butanol.
Not all. It's butanol. Okay?
Okay.
And we don't have to tell people it's on carbon 1 because it has to be on carbon 1.
Yeah.
Okay. There's another one we could do for the aldehyde. We could do this. And this would be called methyl propanal. So why is it a propanal instead of a butanal now?
Because you
1, 2,
needed a carbon.
3 carbons.
Mm-hmm.
And where does the methyl have to be? Well, it can't be on carbon 1 because that would be too many bonds. It can't be on carbon 3 because that would be our butanal. Has to be on carbon 2, which is why I don't bother telling people it's on carbon 2, because it has to be there. Now, does this have the correct number of hydrogens? How many on these terminals?
3.
How many on this one?
2,
Sit.
1,
How many there?
1, 1, 1.
So that's a total of 7, right?
Yeah,
And then this guy,
so 8.
and that fits. Now we can't do that with the ketone.
Right.
I can't take this guy off and stick it on the middle carbon because that would be too many bonds. So not only did we get structural formulas for each of these, we actually got all of them.
Yeah.
Now, what are the easier ones to get? The ones where you just make a straight chain. That's my go-to. If they say draw something that's got this many carbons in it, my go-to is that. Now, what is the correct answer? The correct answer would be this. Remember, we cheated by doing the line drawings. So this is the real answer for butanone.
Right.
I'm getting hungry.
Already.
What do you mean already? I haven't eaten anything yet today.
Well, we just started.
What was that?
We just started.
No, we didn't. We've been at it for 40 minutes.
Mm-hmm.
Okay, these are the structural formulas of each of them. Structural formulas and Lewis structures are a lot of work. And when you get used to line drawings, you begin to really appreciate line drawings and how nice they are.
Yeah.
Like for instance, this ketone here and this aldehyde here, when there's straight lines like that, not only are the line drawings easy to do, but they're also three-dimensional. For instance, this ketone is the following. So does that carbon look trigonoplanar?
Yeah.
Now, these other ones should be tetrahedral, right?
Yeah. It's the hydrogen.
So does that look tetrahedral?
Yeah.
Does that look tetrahedral?
Yep.
Am I boring you?
No, I'm just tired.
So this is actually a three-dimensional drawing to me.
Yeah.
When I see this, I see that. And it's the same for this guy here. Where if I'm just going to fill it in, carbon, 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 hydrogen, the zigzag is what really makes it nice. There you go. Three-dimensional butanol.
Can we do this 87?
Pardon me?
Can we do 87?
Okay, I get it. Let's move on, Tony. 87. Draw structural formulas for possible isomers of the dichlorinated propane. Name each compound. Isomers of the dichlorinated propane.
So the name of this would be dichloropropane, right?
Right.
Okay.
For the beginning part.
Beginning part.
Yep. So here, it does say structural.
Yeah,
So we'll go ahead and start with line drawings and then turn them into structurals. So what am I going to start with?
propane.
Okay, where am I going to put the chlorines?
One at each end.
Okay, that's fine. And when we fill it in, it becomes this. What is the name of this one?
1,3-dichloro propane.
Excellent. Okay, is there any other place we can put these chlorines?
On 1 and 2.
Okay, and when we fill this out, I'm going to fill this one out a little bit differently than I did the other one. And instead of putting the chlorines to the left and right, I'm going to put them above so you can see that they're clearly on 1 and 2 because they're kind of side by side.
Yeah.
And what's the name of this one?
1,2-dichloro propane.
Excellent. Any others that we can come up with?
No.
What about this one?
Oh, 1,1.
Why not?
I don't know.
Well, then if you don't know, then we should have it. Any others?
I guess could we do 2,2-dichloropropane?
Only if there are 2 hydrogens on propane that we could take off and put chlorines on instead. Are there 2 hydrogens on that middle carbon?
Yeah.
Okay, we can take one off, put a chlorine, take the other off. So yeah.
Okay.
So my usual way of doing these when I have 2 to put on, I usually try to put them both on carbon 1. That's what I do.
And
That
then
way
move
I don't miss any of the 1-1s or whatever. And then I keep one on carbon 1 and move the other one over.
Yeah.
And then once I'm done with those, I put them both on carbon 2, and then I keep one on carbon 2 and move it over to the right, the other one to the right. But you can see if we kept one on carbon 2 and move the other one over here, that would just be a 1-2.
Yeah.
So these are all of the structural isomers of the dichlorinated propane and their names.
All right. How about number 99?
How was that a hard one?
Yeah, I was thinking that too. Now it was
Number 99.
I don't know what Markov-Nikov's rule is.
The product of addition of an alkene is often predicted by Markovnikov's rule. Draw the structure of the product of adding HBr to propene and give the name of the product. So Markovnikov's rule is that when you add the hydrogen and the bromine, the hydrogen usually goes to the carbon with the most hydrogens.
So the hydrogen goes to
Yeah. So here, if we take a look here,
the CH.
go back here to I'm sure they explain it in the book. So we're looking at alkenes here, right?
Mhm.
During the 1960s, Vladimir Markovnikov examined a large number of alkene addition. In the cases in which two isomeric products were found, he found that the one more likely to predominate. Based on these results, he's got Markovnikov's rule, which states when a reagent HX adds to an unsymmetrical alkene, the hydrogen atom in the reagent becomes attached to the carbon that already has the larger number of hydrogens. So that means the Br adds to the other carbon.
So I think I know how I'm going to draw this.
So what number was this? 99?
Yes.
Okay, so we're going to use Marky Mark's rule. Markovnikov.
The Russian. Did we just say that?
What's that?
Did it just say that he was Russian?
Oh, yeah.
I feel
With
like there's a lot of Russian.
Vladimir, he's got to be Russian, right?
Yeah. I
He's Russian.
feel like Russians like chemistry.
Russians are responsible for a whole lot of stuff that's been found in chemistry. Germans also, but people from the United States too. A lot of Japanese chemists, Chinese chemists. You know, France, you've got Marie Curie, right?
Yeah.
All countries have contributed greatly to the science of chemistry. People from all countries. Okay. All right, so we're going to use the Marky Mark rule with this hydrogen adds to the carbon with the most hydrogens. Now, that's the product that dominates. That's the major product, not the only product.
Okay.
So, draw the structure of the product by adding HBr to propene. So add HBr to propene. Now it says draw the structure, but it doesn't say structural formula. So we're in luck. But the structural formula might be helpful. So do we agree that this is propene? So we could get two products here. One product could be where the hydrogen adds to the first carbon and the bromine to the second. The other product could be that the hydrogen adds to the second carbon and the bromine adds to the first. So let me just show you what I mean here. Do you see how if we have HBr like this and it combines, the H goes here, the Br here?
H.
And if we have HBr like this, the H goes here and the Br goes there.
Okay.
So do you understand the hydrogen could go to either carbon? The
Yeah.
bromine goes to the opposite?
Yeah.
Okay, so this is how they would be drawn.
Okay.
Okay, which one would be the major product?
The one that was added to.
We'll call this the first one or the second one.
The one that had the most carbon hydrogens to begin with.
Okay, so which carbon, the first one or the second one, has the most hydrogens?
The second one.
No. This has two hydrogens. This has one hydrogen, right?
Yeah.
Okay, so the hydrogen goes to the carbon with the most hydrogens.
I was getting it mixed up that we add the bromine to the one with the most hydrogen.
Nope. The way to think about it is the hydrogen wants to be with his buddies.
Right.
And the biggest amount of buddies because it's a better party with more people.
So then the first product would be the one we're looking for.
That's the major. And what do we call the other one?
I don't know. Minor?
Minor.
Okay.
And what is the name of the first one?
Um, 2 bromo propane.
That's right. And the name of the second one?
So bromo propane. 1 bromo.
1-bromopropane.
Okay.
Okay, so that's A. B. The structure and the name of the compound that results from adding H2O to 2-methyl-1-butene. Okay, so how do you want to draw 2-methyl-1-butene?
So I have our 4-carbon chain with the alkene on the first carbon
Okay,
and methyl on carbon 2,
so something like that.
precisely.
Don't you love, you're really liking these line drawings, aren't you?
Yep.
They're efficient.
Yeah.
Okay, now we're going to add H2O and we're going to get 2 products.
So are we going to break? Oh, wait. I don't know.
So we break the double bond and now we have a single bond there. Where
Right.
does the H go and where does the OH go? Could the OH go on carbon 1?
Could the what?
OH go on carbon 1? Because you see
No.
an H and an OH.
Right.
So could the OH go on carbon 1?
Well, I want to say
Yes.
no because
No, it can.
okay.
The H goes to one carbon, the OH goes to the other.
Yeah, but how do we know which one goes where?
Well, that's what we're going to figure out in just a moment. Could the OH go to the second carbon?
Well, there's 3 bonds there and it needs another one.
Well, the simple answer is if it's a double bond, the OH can go there.
Okay.
So it can go there. Now, in this case, do you see how this beginning carbon has 2 hydrogens bonded to it?
The reactant, yes.
And you see here in this product, it now has 3.
Yes.
That means a hydrogen added there while the OH added there. Are you with me?
Oh, yeah.
And you see how this has 2 hydrogens here and here in the product, it still has 2 hydrogens?
Ooh. With the addition of OH?
Yeah.
Okay, yeah.
But then when we go to carbon number 2, this carbon number 2 has no hydrogens in the reactant, but in the product, it has 1 hydrogen.
Yeah.
So that means an OH added to carbon 1 and an H added to carbon 2.
Okay.
Okay, so which one's the major and which one's the minor?
So the one where we add hydrogen to the carbon that had the most hydrogens.
So does carbon 1 or carbon 2 have the most hydrogens?
Carbon 1.
So that's the major product. We add hydrogen to carbon 1. Which of these 2 products is hydrogen added to carbon 1?
The first one. No.
Okay,
Yes.
so what we're looking for is the number of hydrogens changes, right? How many hydrogens there?
2,
How many there?
3.
I only see 2.
Well, with the OH, no.
The H on the OH doesn't count as a hydrogen on that carbon,
Right.
okay? Because otherwise we'd have to count the hydrogens over here also.
Okay.
So how many hydrogens on that carbon there that I'm pointing at that my finger's going up and down on?
2,
How many there?
2.
So did any hydrogens add here?
No.
Okay, let's go over to here. How many here in the reactant?
2,
How many in the product?
3.
Did a hydrogen add there?
Yes.
Okay. And now go to the second carbon.
Right.
How many hydrogens in the reactant?
0.
How many in this product that I'm pointing at?
1.
1. So a hydrogen added there, didn't it?
Yes.
How many here in the reactant? Second carbon.
How many hydrogens?
Yes.
None.
How many hydrogens on the second one here?
1.
None.
None.
Because here,
OH.
a carbon,
Yeah.
that's a carbon, that's a carbon, and that's an oxygen.
Yeah.
So there are none. So we didn't add any hydrogens there. So which one of these shows the product where we added the hydrogen to the most number of hydrogens? Well, let's take a look. How many hydrogens again on carbon 1?
2.
How many on carbon 2?
None.
Which is bigger, 2 or none?
2.
Where do we want to add the hydrogen? To 1 or to 2?
Carbon 1.
So which one of these shows carbon 1 getting another hydrogen?
The second one.
And that's the major.
Can we do another example?
Well, let's take a look at what C says. C says if you add H2O to 2-methyl 2-butene, is the product the same or different than the product from the reaction in part B?
Is the product the same or different?
So what we're going to do is rather than say, yeah, it's the same or yeah, it's different, we're going to say, you know what? Let's just get the product or products. So how do you want to draw 2-methyl 2-butene?
Butene with the alkene on carbon 2 and methyl on carbon 2.
Okay. Now we're going to add H2O. Draw the 2 possible products.
So it has to be on carbon 2 and 3, right?
That's right. And we're adding an H to carbon 2 and 3, and then an OH to the other side.
Yeah.
So what do you want to do for this first one? Do you want to add the OH to carbon 2 or to carbon 3?
I did carbon 3.
Okay, so right here.
Yeah.
Some people like to do this. So you can see that a hydrogen has been added to carbon 2.
That helps.
Okay, so where did you put the OH on this other side, on this other product?
On carbon 2.
Okay, so what am I going to draw down here below to show that the hydrogen added to the other carbon? This.
H.
Okay,
Hydrogen.
so which one's the major and which one's the minor?
Okay. So carbon 2 has 1 hydrogen on the reactant side. No, it has no hydrogens.
0 hydrogens. And how about the third carbon?
It has 1 hydrogen.
Okay, so where do we want the hydrogen to add to? Carbon 2 or 3?
Carbon 3.
Okay, and if the hydrogen adds to carbon 3, where does the OH add to?
Carbon 2.
Okay, which one of these has carbon 2 with the OH?
The second one.
So this is the major, right?
Yes.
And this is the minor, right?
Yeah.
So they want us to compare the majors of each of these reactions, because they're basically saying, you know what, when you do this reaction, you only get one product. It's not true, but we're going to go with what they think. Clearly, this guy's not an organic chemist. So are the major products of these reactions the same?
Yes.
Yeah. In fact, what would you call this product? You'd call it 2-methyl-2-butanol.
Yeah.
Can you see that based on the structure?
Yeah.
What would you call this one?
2-methyl-2-butanol.
And it doesn't matter whether I have the OH going to the left or to the right. Or, as a matter of fact, whether it's a HO or an OH, right?
Right.
What would the name of this minor product for the first reaction in B be called?
Would it be 2-methyl-1-butanol?
Yes, it would.
Okay.
And it makes sense, doesn't it?
Yeah.
How about this product here? What would this one be called? It's tricky.
2-methyl-1-2-butanol?
You're going to call that carbon 2 and that carbon 2?
No, I'm not.
You just did.
I know. So we want the functional group to be the lower number. So it would be 3-methyl-2-butanol.
That's right. You were trying to, what's the saying?
I don't know.
Have your cake and eat it too. I'm not sure what that means. By giving them both 2s.
Yeah, usually when you have cake, you eat it. So
Yeah, I don't get that. It's a stupid saying. Yeah, I'm going to have my cake and eat it too. What are you
that's why
talking
I got it.
It's probably one of those old French sayings, like Marie Antoinette. She said, let them eat cake. And apparently that was like, saying something bad, like, oh, let them eat dirt. I don't know why. I mean, when she says, if I'm a peasant, she says, let me eat cake. I'm thinking, right on. Thank you.
Hey, there's a chapter on biochemistry.
Yes, there is. And mind you, biochemistry at Humboldt State is taught over a year.
Yeah, there's 2 semesters.
Yeah. And they also have a 1-semester course. And
They
here,
all have what?
a 1-semester course.
Mm.
And here we have what? 1 chapter dedicated to biochemistry. And they try to jam a lot of stuff in here. A lot.
I assume it's trying to give you a very overview, like an overview of it.
But it's a very dense chapter.
Yeah.
Very dense.
Well, that's cool.
All right. Was that it?
Yeah, that was all I had circled.
Okay. Well, I think you've done very well. Looks like you're getting really prepared for this exam.
Yeah, I need to, I would like to maybe go review the previous chapters.
We can do that. If you're the only one calling in, I'll do whatever it is that you'd like to do that would help you.
Okay, right.
Okay.
All right, I'll be here tomorrow. Not Thursday or Friday though. I have to work again.
Well, you're putting the time in and I can see it.
Bring my chemistry book to work with me.
You're probably teased a little bit at work, aren't you?
Yeah, but I don't care. It's okay.
Have any of your colleagues had to take chemistry?
Yeah, the physician.
And what do they say about their chemistry? Easiest class in the world.
No. Mm-mm.
They kind of see your book and then they kind of walk away and start shaking and go,
Yeah, she's all, oh, nice, pretty pictures.
well, did you tell them that your professor said the first thing you do when you look at the book is to look at the pictures?
No.
Because that's what I've said. Look at the
Yeah.
picture, get some background information,
The diagrams, yeah.
and then look at problems. Don't even read the book.
Yeah.
Because when you read the problem, you'll figure out where in the book you need to read.
Yeah, makes sense.
Yep. Because otherwise, it's kind of like reading a novel. You don't know what the important things are. Someone, characters introduced, you don't know they're important or not. You don't know till the end of the book.
Right.
And then sometimes with me, when I read a book, they introduce some character and they give them a name, and they don't use the name very often thereafter, but they're in all the scenes. And I'm like, who is this person? What's their name?
Yeah.
This doesn't work for me. So it works if I know what's important by the questions at the end.
Yeah. Then you kind of can tell what you need to spend time on.
Yeah, exactly. It's a guide. All righty. Well, you've done good. Hopefully, we'll see you tomorrow.
Yep.
And I will post this later today.
Okay. Thanks.
Have a good day. Bye-bye.